everyone, welcome to your lab 7, which is direct shear test. So direct shear test is performed to find out the shear strength of the soil. The strength of the soil is that the maximum stress the soil can bear before failing. For any type of geotechnical structures, it is necessary to know the shear strength of your soil. That's why you can determine what is the maximum strength your soil is going to bear. Direct shear is a quick and an inexpensive method used to find out the shear strength of the soil. But one of the disadvantage of direct shear is that it tends to fail the soil in a designated plane, which will not be the weakest one. So the objectives of today's lab are to calculate the initial void ratio of the soil, to plot shear stress versus your horizontal displacement, to plot the shear stress versus normal stress, then to find the friction angle and cohesion, and finally to find the change in volume. The first objective, that is to calculate your initial void ratio, can be determined by using this equation. So you need to know the specific gravity, the unit weight of water, and also your soil density. The soil density can be measured by getting the soil weight divided by the volume of your soil. From that, you can get the initial void ratio of the soil specimen that you are going to use for the experiment. So this will be the simple representation of your soil. So you will be having a soil divided by two layers. So you will be sliding these soils. So you will be applying an external normal force which will give you the normal stress, and then because of the sliding you will be developing shear stress. The objective is to plot the horizontal displacement versus your shear stress. So we can distinguish the behavior of loose sand and dense sand from this plot. You can see when you shear a dense sand, the shear stress is going to increase with your displacement. At one point you will have a peak, and then your soil is going to kind of fail. But for very loose sand, you will not see a peak failure. It will be continuing increasing. But at one point, this both graph is going to meet at some point. So the next objective is to plot normal stress versus your shear strength. So we'll be using the molecular failure envelope for plotting this. So when from the plot you can see that for coarse-grained soils, the cohesion intercept will be like 0. But for some typical soil, there will be some cohesion intercepts. And from the gradient of these slopes, you can get the friction angle. So from this experiment, we will be able to plot normal stress versus your shear strength by dividing the normal force by the area and by the shear force by the area. Then from the plot, you can find out the cohesion intercept and also your friction angle. And your final objective will be the change in volume. Change in volume can be simply calculated by getting the change in the height multiplied by the area. So change in height will be get from the test. So this will be our shearing ring that we'll be using for our experiment. So initially we need to get the height and also the diameter. So diameter is pretty straightforward. You can just measure diameters. You can get like couple of readings and get the average value. And for getting height, it's a little bit tricky. Like there will be a porous stone on the top. So there will be a line mark over here in a black line. So you need to leave space for the porous plate and then get the height very carefully. It is better to get more readings to reduce the error, because like the porous plate surfaces will not be much horizontal. So I will recommend to get more readings so that you can get the average, so it will be more accurate. First, let's dismantle the shearing apparatus, and we'll be using a dry soil. So first, for determining your void ratio, you need to measure the weight of the soil needed for filling the shear apparatus, and also you need to take measurement of your diameter and height you are going to fill. So initially what I'm going to do is I'm going to fit on this one, and there are two rings on this. You can see one with a black and then one with a yellow, and in this bottom you have holes only for the black rings and not for the yellow one. The purpose is black rings is to hold these two together, and the purpose of a yellow ring is to provide some spacing when you have shearing. So I'll tightly put these black rings. Now I'm going to pour this soil into this apparatus so that I will have space for the porous plate which will be coming on the top. So I'll make sure it is loosely compacted so that we can get the soil strength properties of loose soil. If you want to compact it more, then you can get the properties for the dense soil. So there will be a porous plate on the top. So leaving a space for the porous place, we can fill the soil into this specimen. So to get the weight of the soil that we are going to be using for the experiment, at the start you can measure the total weight of the sand, and then after adding to the specimen, then you can measure the weight of the resting sample. So finally you can find how much sand was filled inside the shearing. Then after adding the soil, I'm going to like loosely compact it, and then I'm going to be placing the porous stone on the top. Then there will be a top part and I will have it there. So we have prepared the specimen, then we'll be moving to keep that in the computer. This is the automated system we will be using for conducting this direct shear test. So before conducting the test, we will be like calibrating the one sensor and then the load cells we have. So one sensor is used for measuring the displacement, initially how much your soil is settling. Then we will be using another sensor for the vertical load, which will be the normal load we will be applying. From that we can find the normal stress. The other one will be the horizontal load cell, where we will be shearing this specimen. So this load cell will move horizontally. So from that we can get the shear stress. So what we have to do first is we have to go to the sensors, and then we got to get all these sensors. And first initially it is must to make sure that the correct sensor is connected by checking their IDs. Then we will be moving for testing and taking zeros for each sensors to make sure there are no loads are applied. So we will do for all the 3 sensors and take down the 0 readings. Once you have calibrated your sensors and the load cells, what we are going to do now is going to place the shearing inside this apparatus. So make sure to place it correctly. Here we go. Now this shearing is placed, so we are going to move this one down. We have placed the shearing, so we are going to move this load cell down so that the distance between these two is like 1/16 of an inch. Observe it very carefully. Once we have adjusted the vertical loading cell, now what we have to do is we are going to have a reaction arm between your shearing and then the horizontal ring. So we will be placing that, and then make sure to tighten it using a screw. We have set up the apparatus, so we are going to be running the shear test. So what happens in running a shear test? First, the load will be applied and a consolidation will take place for this soil. But as we are using a sand and also it's a drain, the consolidation will be very fast. That will be within very few minutes, not like clay. So after the consolidation part is done, the soil will start to shear. So at the end of the reading, we will be getting all the deformations and the stresses from the computer.